Hi, this is Les and Amy from the RevGenetics Podcast. You can listen to the podcast on YouTube and now on Spotify, where we do a deep dive on supplements and longevity studies.
Today we're looking at a really fascinating collision of two different worlds. You've got advanced supercomputing on one side and traditional herbal medicine on the other.
And they're teaming up to fight what is, I think we can all agree, the absolute worst house guest you can have.
The winter vomiting bug.
Yes, the dreaded norovirus. I feel like everyone has a horror story about this. It's that thing that just sweeps through a school or a cruise ship and, takes everyone down.
It really does.
But what's so wild about this study is where the potential cure comes from. It's not some new lab-created chemical. It's stuff you can find in strawberries and ginger, and they found it using computer simulations.
It's a completely innovative approach. We're unpacking a study that used these high-tech digital models to screen natural compounds, basically trying to find a way to stop norovirus before it even gets started.
Okay, so before we get into the computer magic, let's talk about the villain here, norovirus. I mean, we joke about it being the stomach flu, but looking at the numbers in this study, it's actually a pretty serious problem.
It's huge. And you're right, stomach flu is a bit of a misnomer. It's not influenza at all. It's acute gastroenteritis.
Which means?
It just means severe inflammation of the stomach and intestines. And while, for a healthy adult, it's usually just a miserable couple of days, globally, it kills over 200,000 people a year.
200,000, wow. Okay, that is way higher than I would have guessed.
Yeah, it's mostly young children in developing countries and the elderly. They just can't handle the dehydration that comes with it.
And the reason we're even talking about this is because, and this seems crazy to me, we don't have a vaccine for it or even a specific medicine.
Nothing. We have nothing specific to treat it once you get sick.
Why? I mean, we could put a rover on Mars. Why can't we stop a common stomach bug?
It all comes down to its disguise. The virus is a master of changing its appearance.
What do you mean?
It changes its genetic makeup so incredibly fast that by the time scientists even get close to making a vaccine for one version, the virus has already put on a completely new mask.
So it's like a bank robber who gets plastic surgery every single week. The police sketch is always out of date.
That is the perfect analogy. So because that traditional way of making drugs just takes too long, these researchers in Bangladesh tried something totally different. They didn't start with test tubes or petri dishes.
They started with a computer.
The term they use is in silico.
In silico. I love that. It sounds so sci-fi, but it means on a computer, right?
Yeah.
Like silicon chips.
Exactly. Instead of testing all these chemicals in real life, which is slow and expensive and messy, they built a simulation. Think of it like a flight simulator for a pilot.
Okay.
You don't learn to fly a jumbo jet by just, hopping in a real one and hoping for the best. You crash the digital plane 1,000 times first because it's safe. And it's fast.
So in this case, the plane is the virus, and they're crashing different plant medicines into it to see what happens.
Precisely. They built an incredibly detailed 3D model of the norovirus. Then they took 3D models of 59 different chemical compounds from local plants and just virtually threw them at the virus to see if any would stick.
Like a digital puzzle. They're seeing if the plant piece fits perfectly into the virus puzzle.
Yes, and they were targeting two very specific puzzle pieces on the virus. If you want to stop a car, you can, say, slash the tires, or you can steal the engine key. They were trying to do both.
Okay, let's break those down. The study uses some fancy acronyms, but we can simplify it. The first target is what you called the grappling hook.
Right. Technically, it's a protein called VP1, but grappling hook is the best way to visualize it. It's this spike on the outside of the virus.
And that's what it uses to grab onto our cells.
Exactly. The virus uses this hook to grab onto human cells and literally pull itself inside. So if you can block that hook...
It just bounces off. It can't get in?
It can't get in. That's target number one. Target number two is what I like to call the photocopier.
The photocopier. Okay, I'm guessing this is for after the virus is already inside the cell.
You got it. The technical name is RDRP, but it works just like a copy machine. Once the virus breaks into your cell, its main job is to make millions of copies of itself so it can spread. This little machine is what reads the viral instructions and prints out new viruses.
So the whole strategy is either gum up the grappling hook so it can't enter, or jam the photocopier so it can't multiply.
Or, ideally, do both. And this is where the plants come in. The computer simulation ran all 59 compounds, and it found 5 specific winners.
And these come from things like ginger and strawberries.
You know, it's funny you say that. My grandma always gave me ginger ale for a stomachache.
Turns out she was a scientist and didn't even know it.
She was onto something. One of the top compounds is called zingaberol, which, as the name suggests, is from ginger. The computer showed it sticking really, really tightly to that photocopier part of the virus.
So the ginger molecule gets stuck in the gears of the copy machine.
That's exactly what the simulation predicts. It jams the machine. And then another one, phazatin, which you find in strawberries and apples.
And what did the strawberry molecule do?
That one was a champion against the grappling hook. Think of it like putting a tennis ball over a sharp spike. The spike is still there, but it can't really stab anything anymore because it's covered up.
That's such a great image. So you've got strawberries covering the hooks and ginger jamming the printers. And the computer predicts this works even better than some standard drugs.
In the simulation, yes, the binding energy, which is just a fancy way of saying how tightly it grips on, was incredibly strong. But maybe the best part, the computer also ran a safety check.
Right, because, bleach kills viruses too, but you're not going to drink bleach.
Exactly. So the computer analyzed the chemistry of these plant compounds, and it predicted that they're safe. They aren't toxic to the liver, they don't seem to cause cancer, and our body should be able to absorb them easily.
So we have a safe, natural solution that attacks the virus on 2 fronts, all found by a supercomputer. That's amazing.
It's a really promising start.
Big thanks to RevGenetics for helping us unpack today's deep dive into natural solutions.
RevGenetics has been dedicated for years to identifying these evidence-based natural compounds, things like micronized resveratrol and NMN, that support healthy aging.
And it fits so well here because just as they're looking to nature for longevity, this study is looking to nature to fight off viruses.
It's a great reminder that sometimes the most advanced solutions are, hidden in the plants we've been walking past for centuries.
So this all sounds incredible. Strawberries and ginger potentially beating a virus that sickens millions. But we have to talk about what this means for the future. Why is this computer method such a big deal?
Well, it really comes down to 2 main things: speed and cost. Traditionally, finding a new drug is just incredibly slow. We're talking 10 to 15 years.
And billions of dollars.
Billions. Because they have to test every single chemical by hand in a lab.
Which is like looking for a needle in a haystack while you're wearing mittens.
That's a great way to put it. You test one, it fails. You wash all the test cubes, you try another one, it takes forever. This method, computer-aided drug discovery, it lets scientists just burn through that entire haystack in seconds.
They took 59 plants and found the best 5 almost instantly.
Instantly. And that's revolutionary. It means if a brand new virus pops up next year, we don't necessarily have to wait a decade for a solution. We could run the simulation overnight.
It creates a kind of rapid response system.
Exactly. But there's another huge benefit here, and that's accessibility. These compounds aren't some rare synthetic chemical that costs a fortune to manufacture. They come from plants.
Right. We're not mining for diamonds here. This is stuff that grows in the ground.
And that means if these compounds ever become medicines, they could be affordable. The study authors were really passionate about this part. Since norovirus hits developing countries the hardest, having a cheap plant-based medicine could literally save thousands of lives where people can't afford expensive drugs.
That's such a great point. So it democratizes the cure.
Yeah.
And you mentioned earlier that some of these plant compounds hit both targets on the virus. Why is that so important?
Yes, that's the broad spectrum potential. In the simulation, some of these compounds didn't just stick to the grappling hook or the photocopier. They stuck to both. We call that a double tap.
Sounds like something from an action movie, the double tap.
It kind of is. If you only attack a virus in one spot, it might just mutate and learn how to dodge that one attack.
Right.
But if you hold it down by the arms and jam its internal machinery at the same time, it is very, very hard for the virus to escape. You've basically cornered it.
That makes total sense. But, okay, we have to be realistic here. This is all done on a computer. This is what we call the Minecraft reality check.
Yes, exactly. The Minecraft reality check. You can build a magnificent floating castle in Minecraft. The game's physics say it works. It looks perfect. But if you try to build that same floating castle in your backyard with real bricks...
Gravity is going to ruin your day.
Gravity is going to ruin your day. So just because the strawberry molecule sticks to the virus in this perfect, clean computer simulation doesn't automatically mean it's going to work in a messy human stomach.
Right. Our bodies have stomach acid, enzymes, an immune system, all kinds of things going on.
Correct. The computer simulation is a perfect vacuum. So the very next step is what's called the wet lab.
Time to get their hands dirty.
They need to take real norovirus, put it in a real dish with these real plant extracts, and see if the virus actually dies. And then eventually you move to animals and then humans.
So it's not a finish line, it's more like a treasure map. The computer just told us, dig here.
Exactly. But that alone saves years of digging in all the wrong spots.
I love that. And if it works, let's dream for a second. What's the best case scenario here?
Imagine a future where your kid comes home from school and says, Mom, Dad, 3 kids threw up in class today.
Oh, I know that feeling of dread. You just start washing all the sheets preemptively.
You do. But in this future, maybe you just open the medicine cabinet and pull out a little supplement derived from these exact plants, super concentrated ginger or ficitin. You give it the whole family.
And so when the virus shows up and tries to use its grappling hook on our cells,
It finds the lock's already taked over. It just slides right through your system. You never even get sick. You break the chain of infection entirely with something safe and natural.
that is a future I want to live in. It's just amazing to think the answer might be growing in a garden right now.
It really reminds us that nature is this massive, massive library of solutions. We've only read a few of the books, and computers are finally giving us the glasses we need to read the rest of that library.
I'm never going to look at a strawberry the same way again. It's a little tasty warrior.
This just might be.
We hope you enjoyed learning about this recent research and found it as fascinating as we did.
Thank you for listening to the RevGenetics Podcast.
RevGenetics.com for the best longevity supplements on Earth.